So David in his opening keynote mentioned the importance of the history of compute and how we should learn from it and guide our way into the future. And in similar spirit, I'll be talking about something which I feel is often overlooked as an area of research, web archiving, the challenges faced by web archiving, and what we as systems researchers can do to overcome those challenges. Specifically in this talk, I'll be focusing on how to reduce the storage overhead incurred by web archives and simultaneously improving the quality with which these pages are archived. Now, before I dive into the technical details, let me take you guys on a time travel trip to a week after the conference. Turns out that all the amazing research that I presented today, it caught the attention of a bunch of news journalists. It caught the attention of a bunch of news journalists all across the internet. And New York Times decided to cover my article, my research in an article. And a couple of other news websites like Hacker News and Michigan CSE website followed suit, and they published an article covering my research. Now, naturally, I'm very happy, and I decided to add links to these news sources from my personal homepage so that anyone who decides to visit my page can check out all the media coverage that my work is getting. Now, let's go 10 years from now in the future. The year is 2032. Some PhD student stumbles upon my personal homepage. They come across all this media coverage that Java is getting, and they decide to visit those links. However, it turns out that they cannot find any of those links anymore. Some of the sites stopped hosting those pages, and some of the sites itself just ceased to exist. Now, this problem of link rot, that is, a link that is created today might not exist at some point in the future. And to show how prevalent this problem is, Wikipedia has a dedicated article which contains all the permanently dead external link. In light of this, there have been a lot of studies that focus on measuring the impact of link rot in various reputed journals like New York Times and various different scholarly articles. Now, to combat this problem, a lot of web archives have been set up. To name a few, Internet Archive, Library of Congress, the UK Web Archive. I'll give you a brief glimpse of how these web archives really work. Internet Archive provides a Wayback Machine where the user who's trying to find a particular web page can enter the URL of one of these pages. Thereafter, the Internet Archive would load a version of this page that is stored on their storage servers and hosted by them. Internet Archive is currently the biggest web archive. It stores about 700 billion pages, amassing to about 100 petabytes of storage. Now, let's talk about how these modern web archives operate internally. Most of them, they consist of a crawler that could be browser or non-browser based. They interact with web pages on the live web, and as a result, fetch all the underlying resources such as HTML, JavaScript, CSS images. Thereafter, they apply certain deduplication and compression techniques so as to reduce the storage overhead of saving these resources. And at some distant point in the future, a user willing to visit these archive pages will fetch these underlying resources, parse them, and render them in a manner identical to how it would if it would have loaded this page from a live web. Now, it turns out that the status quo of web archiving suffers from various fundamental problems. First, for a large fraction of pages on the web, not even a single snapshot exists on any of these archives. For example, if you were to query the Internet Archive with one such URL, it will respond with a message saying that this particular page was never archived before. A second and even bigger problem is the fact that for a lot of pages that these archives indeed have archived, they render with poor page fidelity. For example, here are the screenshots of two pages loaded from Internet Archive. And as you can see, for both of them, a number of critical resources, such as images and text, is missing. So let's recap real quick. So far, I talked to you guys about why web archiving is important and the challenges faced by it. Let's move on to understanding the fundamental root cause behind these challenges. Turns out that the increasing amount of JavaScript on modern web pages is the real cause and the contributor for both of the previously mentioned challenges. To understand this, we conducted a study with landing pages of 300 Alexa sites. And for each of these sites, we looked at the total page size across 3 different decades. As you can see from this graph, the total page size, that is bytes on these pages, have been continuously increasing. Turns out that this increase in the number of bytes on the page can be strictly correlated with the increase in the number of JavaScript bytes on these pages. Because of these, snapshotting these pages or archiving these pages incurs more storage overhead, and as a result, these archives can store only so much snapshots. The second negative impact of JavaScript is the inherently induced non-determinism. A lot of you must be aware how when you load a given web page on different devices, the page renders differently. How does this work? Client-side JavaScript inspects the client device information and as a result decides which URLs to fetch. Similarly, a lot of web pages today offer light and dark mode. In order to implement this, they basically inspect the client-side cookies, check for user preferences, and accordingly fetch light.css or dark.css. So with the help of these examples, I'm trying to demonstrate that these non-deterministic APIs influence what URLs will be fetched. Now, this becomes a problem in the case of archived pages because the set of URLs that are crawled might be different from the set of URLs that get fetched because of these different values of sources of non-determinism. Next, I'll talk about the insight that we leverage to solve the above problems. Turns out that the key insight that we use to develop a new crawler is the fact that archive pages load fundamentally different from live pages on two different fronts. First, in the case of an archive page, there is no backend origin server. To understand this, let's look at the same page of New York Times from earlier. As you can see on the top left corner, there's a search query where the user can input a query and retrieve similar articles. Now, this functionality is implemented using client-side JavaScript, which interacts with the backend server and retrieves similar articles. Now, in the case of an archive page, this backend server doesn't exist, and therefore this functionality wouldn't work. Turns out that modern pages have a lot of similar functionality, like the ability to add comments to the pages logging in. Therefore, all this JavaScript that interacts with the backend server will never work, and you can remove it without degrading page fidelity. The second point of difference is the fact that certain sources of non-determinism are absent in the case of an archive page. To understand this, let's again look at a snippet of JavaScript code from New York Times. There's this function called isUserSubscribed, which inspects client-side cookie and checks for an authentication token. If this token exists, then it will print the account info, and if the token does not exist, then it will simply print the login button. Now, in the case of an archive page, this authentication token will never exist, and therefore this function will always take the same control flow. Basically, JavaScript in certain control flows will never be executed in the case of an archive page, and again, you can remove it without degrading fidelity. Now, leveraging all these insights, we have built a new web archival crawler called Java, which stands for JavaScript Aware Web Archive. It leverages two orthogonal techniques to reduce storage cost, that is identifying and removing non-functional code and identifying and removing unreachable code. And it improves page fidelity, that is ensures that the page visually and functionally looks similar to the live version, and it does so by eliminating the impacts of non-determinism. In the interest of time in this talk, I'll only be focusing on fidelity and how to remove unreachable code. Let's talk about fidelity first. So I've already established that the root cause for poor fidelity is JavaScript's non-determinism. So one straw man that one would imagine is to make the page completely deterministic. To show how this fails, I'll leverage an example of a Tetris game that is implemented in JavaScript. This game leverages the random number API to decide which block of Tetris to fetch next. Now, if you were to make this page completely deterministic, this random number API would always retrieve the same value every time, and as a result, the same Tetris block gets fetched. With the help of this example, I'm trying to demonstrate that non-determinism sometimes could be critical to the functionality of the page, and you cannot eliminate it without any good reason. And therefore, it's important to understand how these different sources of non-determinism influence resource fetches. To do so, we look at two different categories of non-determinism. One, date random and performance APIs, which we call as DRP APIs. A second, client characteristics, such as screen dimensions, user agent, and operating system. For both these categories of APIs, we analyze their impact on the control flow of JavaScript execution on a corpus of 3,000 pages, and we make a couple of very interesting observations. First, DRP APIs do not really influence the control flow execution on any of these pages. Rather, they only influence the data flow. And as a result, they do not contribute to poor page fidelity, and Java does not have to eliminate their non-determinism. On the other hand, it turns out that client characteristics were the key contributor to these divergence in URLs. They influence control flow and as a result fetch URLs which were never crawled. And therefore, in order to fix fidelity, Java decides to eliminate any corresponding non-determinism. Now, having fixed fidelity, now let's talk about how Java identifies and removes unreachable code. Again, a strawman approach that one could take is to only store code that was executed when the page was being crawled and throw away all the other JavaScript code. The shortcoming with this approach is that any interaction on the page, which is powered by client-side JavaScript, will not work as all this interaction works after the page has been crawled. For example, the menu button on New York Times. Now, identifying all this code that is identifying all the code that powers client-side interaction is challenging for multiple reasons. First of all, it depends on how the user interacts with the page. The first metric is the order of interaction. Here is an example New York Times page, and as you can see, there are multiple elements on the page with which the user can interact with. Now, clearly, some of these events can have read-write dependencies between them with respect to the JavaScript or the DOM state they access. And as a result, the order in which these events get clicked can influence what underlying code gets executed. The second reason why this is non-trivial is because the code executed can also depend on the input given by users. To understand this, let's again look at the New York Times page from earlier and the search button. The user can enter a very specific query such that a single result gets printed, or the user can enter a very generic query such that thousands of results get printed. Now, in the latter case, what happens is that the client-side JavaScript paginets the response and adds a show more button. Now, it's clear that the input that the client gives dictates what client-side JavaScript gets executed. Now, in order to estimate all these code covered, it is impractical to explore all these different interleavings of orderings and the input ranges. And therefore, in order to understand these state dependencies between different events on the page, we have built a custom analysis, a JavaScript analysis framework. What this framework does is it's capable of looking at a source code, statically analyzing it, and injecting instrumentation code such that when you execute this rewritten function, you can access all the state it reads to or writes from. Thereafter, after rewriting the entire page, we trigger all the interactions on the page, and we monitor the corresponding state accesses. And we run this analysis on a corpus of 3,000 pages from earlier. We find a couple of very interesting things. First, the order of these different events mostly influenced code coverage in the case of analytics events, that is, events that are created by tracker files, whereas input mostly influenced the code coverage for text-based events, such as the search button from earlier. Now, as you can see, both these categories of events are irrelevant in the case of an archive page. And therefore, the strong implication of this observation was that for all the remaining events that are indeed relevant for archive page, identifying code covered becomes very trivial. You just execute all of them once with default inputs. Finally, I'll move on to the evaluation of Java. We evaluate Java's storage benefits, its impact on fidelity, that is the number of failed request fetches, and throughput. For each of these dimensions, we looked at multiple different metrics. However, in the interest of time, I'll only be focusing on 2 of them. In order to evaluate Java storage, we built a new corpus of 1 million snapshots from the same 300 sites that we've been using so far that are archived by Internet Archive. And we looked at the storage overhead incurred only by JavaScript resources for these 1 million snapshots. Turns out that Java reduced the storage overhead for JavaScript by about 84% on account of the 2 techniques, removing non-functional and unreachable code. However, in order to store these 1 million pages, you don't only store JavaScript. You have to store HTML, CSS, images, and other things as well. Turns out that JavaScript is such a big fraction of page bytes, as I showed you earlier, that an 84% reduction in JavaScript resulted in about a 41% reduction in the total storage overhead across all resource types for 1 million pages. Now, one would assume that you have reduced storage, so there's a high chance that you might have degraded fidelity. That is, you might have thrown away certain JavaScript that is critical for the page. And therefore, in order to evaluate Java's fidelity, We look at the same corpus of 3,000 pages from earlier. We crawl them using techniques that are used by Internet Archive, and then we load them again and looked at what fraction of requests failed because of JavaScript's non-determinism. As you can see from the CDF across 3,000 pages, for about 10% of pages, more than 30% of resource fetches failed. When we ran the same analysis with Java, we found out that it eliminated almost all network fetches, failed network fetches. That is, for about 95% of pages, there were 0 failed fetches. This is because of the fact that Java eliminated the non-determinism resulting from client characteristics. In conclusion, I demonstrated how JavaScript on web pages negatively impacts web archival, and there are fundamental differences between live and archive pages that you can leverage to overcome these challenges. The dataset and the code used in our paper is open sourced, and I'm happy to take any questions. Thank you.